Welcome to a journey into the fascinating world of liquid metals. Today, we're exploring how element 31 on the periodic table, gallium, is sparking a technological revolution that could transform everything from medicine to computing. This once overlooked metal, which melts in the palm of your hand at just above room temperature, is now at the center of cutting-edge research worldwide. Scientists are creating self-propelled liquid metal droplets that navigate complex environments, developing soft robots that can squeeze through tiny spaces, and even building computers that process information through the movement of liquid rather than electricity. Join us as we dive into the remarkable science behind gallium and discover how this shape-shifting element is blurring the line between science fiction and reality. Gallium occupies position 31 on the periodic table and possesses a truly remarkable property. It remains liquid at just above room temperature, melting at only 29.8 degrees Celsius. Unlike mercury, which has been used in various applications historically, gallium has low toxicity, making it much safer for biomedical and everyday applications. But what makes gallium truly special extends beyond its low melting point. It boasts exceptional thermal conductivity at 29 watts per meter Kelvin, allowing it to efficiently transfer heat. Perhaps most importantly, gallium readily alloys with most metals, creating opportunities for customized material properties. When combined with indium and tin to form galinstan, the resulting eutectic alloy remains liquid down to -19 degrees Celsius, dramatically expanding the operational temperature range for liquid metal systems. This versatility makes gallium-based alloys suitable for extreme environments, from the freezing depths of ocean exploration to aerospace systems that experience dramatic temperature fluctuations. The most groundbreaking development in gallium research came from Tsinghua University in Beijing in January 2023. Their research team demonstrated the first self-propelled liquid metal droplets capable of navigating through complex mazes in confined spaces without any external power source. These liquid metal robots exploit a fascinating aspect of gallium alloys: their unusual surface chemistry. When placed in an electrolyte solution, these droplets naturally develop an oxide skin on their surface. This oxide layer can be manipulated through subtle pH changes or weak electrical fields. The Tsinghua team discovered something remarkable. By creating asymmetric deformations in this oxide layer, they could induce directional movement. They had essentially created a chemomechanical engine at the microscale, powered by chemical reactions at the droplet surface. Their work, published in the prestigious journal Advanced Functional Materials, demonstrates these gallium-based droplets successfully navigating complex channel networks while carrying payloads up to 10 times their own weight. This self-powered movement represents a fundamental breakthrough in soft robotics and microfluidics. Recent advances in surface chemistry have dramatically expanded gallium's potential applications. Researchers at the Max Planck Institute for Intelligent Systems have pioneered methods to functionalize liquid gallium surfaces with self-assembling monolayers, essentially creating droplets with programmable surface properties. These sophisticated surface modifications give scientists unprecedented control over the droplet's wettability, adhesion, and chemical reactivity. This enables the design of liquid metal systems that respond differently to various biological tissues or synthetic materials. By carefully engineering the surface chemistry, researchers can create droplets that selectively interact with specific environments or substances. This precise control transforms simple liquid metal droplets into sophisticated sensing platforms or delivery systems that can distinguish between different biological environments. These functionalized droplets represent a significant step forward from simple liquid metal beads, offering programmable behavior that can be tailored for specific applications in medicine, environmental monitoring, and advanced manufacturing. Perhaps the most promising applications for liquid metal technology lie in medicine. A groundbreaking collaboration between researchers at the University of California, San Diego and the Shenzhen Institute of Advanced Technology has produced prototype liquid metal microrobots specifically designed for targeted drug delivery within the digestive tract. Their innovative system, which completed preliminary animal trials in March 2023, uses magnetic fields to precisely guide gallium-indium alloy droplets that are coated with drug-containing polymers. These sophisticated droplets can navigate through the complex environment of the digestive system until they reach inflammation sites. Once at the target location, changes in the local pH environment trigger the release of therapeutic compounds directly where they're needed most. This targeted approach could revolutionize treatment for conditions like inflammatory bowel disease, allowing for precise medication delivery with minimal systemic exposure and side effects. The low toxicity of gallium makes it particularly suitable for these biomedical applications, offering significant advantages over other liquid metals like mercury that would pose serious health risks. Environmental cleanup represents another frontier for gallium-based technologies. Engineers at North Carolina State University have developed innovative liquid metal scavengers that can selectively absorb heavy metals from contaminated water sources. These specialized gallium-based droplets are functionalized with chelating agents, chemical compounds that bind specifically to toxic metals like lead, mercury, and cadmium. When introduced into contaminated water, these liquid metal droplets effectively remove harmful substances from the solution by binding them to their surface. The genius of this approach lies in the recovery method. Once loaded with contaminants, the droplets can be easily collected using simple magnetic fields, offering a potentially revolutionary approach to water purification in remote or disaster-affected regions where traditional filtration infrastructure isn't available. This technology could provide rapid response capabilities for environmental disasters or serve communities with limited access to clean water infrastructure. The reusability of these systems makes them particularly valuable for sustainable remediation efforts in challenging environments. The extraordinary versatility of liquid metal systems has captured significant attention from the soft robotics community. Traditional robotic systems face fundamental limitations due to their reliance on rigid components and discrete actuators, which restrict their ability to navigate confined or irregular spaces. Professor Karmal Majidi's pioneering team at Carnegie Mellon University has developed innovative soft robotic systems with integrated liquid metal circuitry that can withstand extreme deformation while maintaining full functionality. Their most recent prototype, unveiled at the 2023 International Conference on Robotics and Automation, demonstrated a remarkable crawling robot capable of squeezing through apertures just 1/3 of its nominal diameter while still carrying onboard sensing and communication systems. This breakthrough in deformable electronics opens possibilities for robots that can navigate environments previously inaccessible to conventional machines, from disaster rubble to the human body. The liquid metal circuits maintain electrical conductivity even when stretched, compressed, or twisted, allowing for electronic systems that move and adapt like biological organisms rather than mechanical devices. Perhaps the most radical application of gallium technology lies in the emerging field of unconventional computing. Traditional silicon-based computing faces fundamental physical limitations as transistors approach atomic scales, with heat dissipation and quantum effects creating barriers to further miniaturization. Liquid metal computing offers an entirely different paradigm that sidesteps these limitations. Researchers at Carnegie Mellon University and the Beijing University of Chemical Technology have successfully demonstrated rudimentary liquid logic gates using gallium alloy droplets in carefully designed microfluidic channels. These liquid computers process information through the physical movement and interaction of droplets rather than electron flow, representing a complete departure from conventional electronics. A team led by Professor Michael Dickey at North Carolina State University recently achieved another milestone by demonstrating a liquid metal memristor, a component that mimics certain neural functions and is capable of learning from previous inputs. Their system, detailed in a groundbreaking paper published in April 2023 in Nature Communications, shows how these liquid circuits can perform specific pattern recognition tasks with significantly lower energy requirements than conventional electronics. The physical dynamics of the droplets naturally implement parallel processing operations that would require significant computational resources in traditional digital systems. The most intriguing aspect of liquid computing is its inherent reconfigurability. Unlike fixed silicon architectures that are etched permanently during manufacturing, liquid metal circuits can be dynamically reshaped to perform entirely different computational tasks as needed. This adaptability makes them particularly suitable for edge computing applications where processing requirements may change rapidly based on environmental conditions or user needs. Professor Andrew Adamatsky at the University of the West of England has proposed revolutionary computational architectures based on collision-based computing, where information processing occurs through the controlled interaction of liquid metal droplets. His detailed simulations suggest that such systems could solve complex problems, particularly those involving spatial navigation or pattern recognition, more efficiently than conventional algorithms. Recent experiments at the Tokyo Institute of Technology have demonstrated simple decision-making algorithms implemented through the controlled merging and splitting of gallium-indium droplets in specially designed reaction chambers. When presented with multiple potential paths, these systems consistently solved maze problems by following chemical gradients, effectively computing optimal routes through physical processes rather than digital calculations. This approach to computing mimics certain aspects of biological information processing, where physical and chemical interactions directly contribute to problem solving. Despite the remarkable progress in liquid metal robotics and computing, significant challenges remain before these technologies achieve widespread deployment. Control precision remains limited compared to conventional robotics, with environmental factors sometimes causing unpredictable behaviors in the liquid metal systems. Scaling production while maintaining consistent performance presents serious manufacturing hurdles that must be overcome for commercial applications. The oxide layer that enables many of these applications is also susceptible to environmental conditions, potentially limiting deployment in uncontrolled settings outside laboratory environments. Material compatibility presents another significant challenge. While gallium's ability to form alloys with many metals offers versatility, it also means that containment systems must be carefully designed to prevent unwanted reactions. Silicon, glass, and specific polymers have emerged as preferred materials for microfluidic systems working with gallium alloys, but this constraint limits integration with existing technologies. Researchers at Lawrence Berkeley National Laboratory are exploring ceramic-based microfluidic platforms specifically designed for high-performance liquid metal systems, potentially offering a pathway to more robust and versatile devices that can withstand a wider range of operating conditions and chemical environments. Researchers are actively addressing the limitations of liquid metal technologies through innovative approaches. A team at the University of Wollongong in Australia is developing composite materials that combine liquid metals with hydrogels to create more stable, programmable structures that maintain the advantages of liquid metals while improving control precision and environmental stability. Meanwhile, scientists at Zurich are exploring ways to functionalize the surface of gallium droplets with DNA-AP tamers, potentially enabling highly specific biochemical interactions that could revolutionize biosensing and medical diagnostics. The field's rapid development has also prompted regulatory attention. In June 2023, the U.S. Food and Drug Administration established a dedicated working group focused specifically on liquid metal medical applications, recognizing both the tremendous promise and potential risks of these emerging technologies. As research accelerates, the coming years will likely see the first approved medical applications, potentially revolutionizing minimally invasive procedures and targeted drug delivery systems. The interdisciplinary nature of liquid metal research is perhaps its greatest strength. Progress requires collaboration between materials scientists, electrical engineers, computer scientists, and biologists. This convergence is driving innovation at an accelerating pace, with breakthroughs in one domain rapidly influencing developments in others. The coming decade will likely witness the emergence of sophisticated hybrid technologies that incorporate both conventional electronics and liquid metal components, leveraging the strengths of each approach. Traditional solid-state electronics offer precision and reliability, while liquid metal systems provide adaptability and novel functionalities that rigid systems cannot achieve. By combining these approaches, researchers aim to create systems with unprecedented capabilities that transcend the limitations of either technology alone. As these technologies mature, they promise to fundamentally transform our relationship with machines, blurring the boundary between the mechanical and the organic. Liquid metal systems create machines that combine the programmability of computers with the adaptability of living systems, capable of changing shape, navigating complex environments, and even healing damage through self-reconfiguration. The field of liquid metal robotics stands as a testament to how materials once considered laboratory curiosities can evolve into platforms for technological revolution. As researchers continue to explore the unique properties of gallium and its alloys, we stand at the threshold of a new era in which machines may flow, adapt, and respond to their environments with an almost lifelike fluidity. This convergence of solid and liquid, of rigid and flexible, of programmed and adaptive, represents not just a new technology but potentially a new paradigm for how we conceptualize and build the machines that will shape our future. Gallium, element 31 on the periodic table, has emerged from scientific obscurity to become a cornerstone of cutting-edge research across multiple disciplines. Its unique properties, liquidity at near-room temperature, low toxicity, high thermal conductivity, and versatile alloying capabilities, have enabled breakthroughs that were once confined to science fiction. From self-propelled droplets navigating complex environments to soft robots that squeeze through impossibly small spaces, From targeted drug delivery systems to environmental remediation technologies, gallium is transforming how we approach some of our most pressing technological challenges. Perhaps most revolutionary is its potential to create entirely new computing paradigms through liquid logic systems that process information through physical movement rather than electrical signals. While significant challenges remain in controlling these systems and scaling manufacturing, the interdisciplinary collaboration driving this field forward suggests these obstacles will be overcome. As we witness the convergence of conventional electronics with liquid metal systems, we're entering an era where machines may possess an almost biological adaptability, flowing, reshaping, and responding to their environments in ways rigid systems never could. The liquid metal revolution represents not just a new set of technologies, but a fundamental shift in our relationship with machines, blurring the boundaries between the mechanical and the organic, the programmed and the adaptive. The future of computing, robotics, medicine, and environmental technology may well flow from this remarkable element that melts in the palm of your hand. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.